Let's talk a little bit about crossed fields. And in this case, we've got a crossed electric field and a magnetic field. So here we've got a magnetic field that is out of the page, right? Remember, those little dots mean the tips of arrows. So the arrows are coming straight at us, right? Now, if we've got a proton, if it enters this field and it's going to the right, like this, okay, that's its velocity. Remember, you can put your index finger this way, right? My index finger is that way. My middle finger is going to point out of the page, right? So make your middle finger, it's a little awkward, I can do it, right? In this case, the force, the resultant force of this, the magnetic force, is this way. This is the way your thumb is, right? So that's the direction of the force. I'll call that the magnetic force, okay? And that's your thumb. Now let's just double check. Let's make sure I got this right. Index finger to the right, okay? Magnetic field out of the page. My thumb is down. Now, normally what this thing would do is it would just sit there and spiral clockwise in the page because of this magnetic field. But if I put a electric field that exerts a force upward, that is, if I put a negative charge up here and a positive charge down there, it's possible to make this thing go straight. Okay, I can make it go straight, and the way to do that is, of course, to make the electric field be up the page, right? So the electric force would be, in this case, up. All we have to do is make the electric force equal but opposite the magnetic force, right? Well, this is pretty simple. The magnetic force is QVB, and let's assume it's 90 degrees so we don't have to worry about the sine of the angle, right? And then electric force is E times Q, right? Well, a super cool thing happens if we set the magnetic force, that's our magnetic force, this is our electric force. If we set the magnetic force equal to the electric force, watch this. Okay, I'm going to go QVB equals EQ. If you're paying attention, I can cancel the charge. So as long as it has charge, okay, we actually can we can do a lot of things with it. Well, one thing is we can find that electric field. The electric field is just V times B, right? Okay, so I can find, you know, what direction is the electric field that would cause this? Well, it would simply be V times B. So let's do that. Let's answer the question. 2.35 times 10 to the 7th meters per second times, and then the magnetic field is 0.0145 Teslas. Let's answer the question first. 0.0145 times 2.35 E7. So the answer to this is that a electric field of merely 340,750 newtons per coulomb up the page would make it go straight, okay? So that's pretty simple. This part's not terribly interesting, right? We can just solve for that. But here's the cool thing, right, is if I solve that for V, okay, V is going to be E divided by B. Now, let's think about that, right? Only particles with that exact velocity, charged particles with that exact velocity, will go straight through this field. Ones that are going faster will tend to curve down, because then the magnetic force would be bigger. Ones that are going slower would tend to curve upward, right? Because the magnetic force would be weaker. The electric force doesn't depend on velocity. It's just E times Q, right? But the magnetic force depends on this, right? It doesn't depend on the mass. I gave you the mass here, right? That's just kind of a red herring. But it doesn't matter the mass. If it goes straight, it's not accelerating. And so the mass doesn't matter. So that's sort of interesting. So you can use these things. You can cleverly construct these. If you make a little slit here, and you make a little slit here on the other side, only particles that are capable of going straight through will make it through this, right? And so you use this. This is actually a velocity selector. All right. Time to teach induction.